Thanks everyone for joining. Today we're going to talk about future-proofing your risk management and compliance with graph technology. First, we're going to look a little bit at some of the regulations that we'll be addressing, financial services industry regulations, and then specifically we're going to focus on FRTB, Fundamental Review of the Trading Book. Then we'll take a few minutes to introduce Neo4j and talk about why our graph database is such a good fit for modern risk management platforms. And we'll do a quick introduction to the Neo4j data model, the property graph, and the Cypher query language before we dive into a demo. And we'll take a look at some samples of how you can use Neo4j to address FRTB compliance. After that, we'll do a quick review, and as Angelica said, we'll have some time at the end for questions and answers. So we can see, the regulatory landscape facing financial services firms today is dizzying. It's an alphabet soup of different regulations, right? We've got BCBS 239, we've got FATCA, we've got MiFID 2. It's quite extensive. And a lot of effort needs to be put into compliance by financial services firms, and it's quite an investment in time and money. But actually, if you dig underneath, a lot of these regulations actually rely on the same data. So it's quite possible to build an overarching system that would address many of them. The principles are really quite similar. You've got risk data aggregation and reporting. These things need to be accurate, they need to be comprehensive, they need to be clear. You need to be able to report clearly to the regulators and the authorities. You need to be able to demonstrate that you have proper supervision and your data governance is in place, right? You understand how your data is moving, you control how it's aggregated and moved through your systems, and you can demonstrate that again to the regulators and to the authorities. Specifically, FRTB focuses on different trading books that an organization might have, right? So you have your banking book, which tends to be lower risk, low frequency of trading. These are usually things that are held until they fully mature. An example might be corporate loans, something like this. And the banking book is treated differently by the regulators than the trading book because it is lower risk and because you do tend to hold on to these things until they're mature. So the capital requirements, the money that needs to be held in reserve to cover, realization of risk tends to be lower for the banking book. The trading book, on the other hand, tends to include assets that are frequently traded, right? Instruments that are frequently traded, like stocks, bonds, options, and they're inherently more risky in the trading book than in the banking book, right? And so the regulators require higher capital reserves to cover that risk for the trading book. But the more capital reserves you have to have as a financial services organization, the less money you have to invest, the less money you can put to work earning money. And so financial services firms usually want to keep capital reserves as low as possible, to operate safely and to meet their regulatory requirements so they can invest as much of that as possible. And this is where understanding your risk reporting and risk aggregation comes into play, right? So the idea behind FRTB is that organizations need to be able to come up with a risk model that they can demonstrate to regulators. They've developed it internally. They can demonstrate that they understand their risk, that they can calculate it and act on it accordingly. And then having that internal risk model means that you can then use a lower capital reserve rate than you might otherwise have to. So if you can put together that model and you can demonstrate it to the regulators and they accept it, you pass, and you can have lower capital reserve requirements, more money for you to invest, and generate revenues and profit. If you can't satisfactorily demonstrate that you have a risk model that will be accepted by the regulators, and you fail, then you have to use a standard BCBS model, which will probably end up being higher capital reserves than you would have liked, or that you would have used under your own model. Meaning that you have less capital for investment, it offers you less flexibility, and that will lead to a lower revenue and lower profit. So financial services organizations will really want to be able to pass this sort of regulatory review, right? And what we'll show later is that Neo4j and our graph database can help with this modeling, help you put together something that will be more likely to pass the regulatory requirements for FRTB. So what we're really looking at, is complex data lineage within the trading book, right? So what we have here on the left in blue are a number of trading desks within an example organization. We have an energy desk, a technology desk, commodities, mortgages, so on and so forth. Each one of those can have multiple things that sit within it, right? So you can have multiple baskets that sit within it. So we can see the energy desk has the batteries basket, so does the technology desk. The technology desk also has cloud computing, so on and so forth. Within them, you might also have indexes, and then ultimately that all flows down to individual equities, individual assets that all have their own pricing and their own risk score that would be assigned, right? So you need to be able to understand from the desk all the way down to the individual assets how you can calculate the risk that's built into each one of these things, and then also go the other direction, right? All the way up from the individual assets through to the desks that trade them or have positions in them. And this naturally represents itself as a graph. As we'll see, if you're not familiar with graphs, we'll get into it in a little while. But this really is a graph model, right? The highly connected nature of this, the way that things can be connected to multiple other items, and the need to be able to trace those connections back and forth, down and up the hierarchy, really is a natural fit for Neo4j and the graph database. Another part of the FRTB requirements are to be able to test the model. So once you have your model established and you understand how you're going to aggregate risk and calculate that, you need to be able to demonstrate that model and that it works back over 10 years worth of data. And then going forward, you need to be able to demonstrate every year using 24 real data points at different dates throughout the year. You need to also be able to demonstrate that your model works and that it keeps the right amount of risk in place, right? So we can see at the bottom, you want your risk really to be in this green zone, right? A low level of risk, a very acceptable level of risk. If it occasionally runs into a medium level of risk, that's okay. But if your organization were regularly reporting high levels of risk, dangerous levels of risk, then you would need to reassess, your risk model and your approach to risk. As I mentioned before, this data lineage has to flow in both directions, right? And you need to be able to demonstrate how that flows in both directions, looking at a trading desk and how that works down to individual assets, and then looking at individual assets and understanding how you aggregate all that risk up the hierarchy to the trading desks. So for those not familiar with Neo4j, Neo4j is the world's #1 database for connected data. We are an enterprise-grade native graph database. So we're architected from the ground up to work with highly connected data and to treat the relationships between data entities as importantly as we treat the data themselves, right? And it allows you to traverse these relationships to great depth, any depth really, in real time, as well as being able to add new data and work with that new data in real time on the fly. And Neo4j offers all of the, the sort of technical design and architecture decisions you would expect from an enterprise-grade database. It's ACID compliant. It has clustering for high availability. We have a suite of developer productivity tools, so on and so forth. So it is an enterprise-grade database ready to handle these sorts of complex risk aggregation calculations for large financial services firms in real time and at the scale of data that these firms would be used to handling. And this is quite a different model, really, from traditional relational databases, right? Traditional relational databases are oriented on tables with columns and rows, great for ledgers and working with large uniform sets of data. But managing highly connected data in a relational database is really difficult. It requires joins when you have to connect lots of data sets, or when you have to connect data sets to themselves recursively. The SQL that generates that query can be quite complex and can be very slow to run. Whereas Neo4j is built to manage highly connected data, and we have our own query language to enable that, which is called Cypher. You can see a sample of it here on the lower right, and we'll get into it a little bit more in a bit more detail in a moment. What the graph database also lets you do is manage data that would traditionally come from a number of different silos within a financial services organization. So you might have separate databases for your trading desks, for fund management in your baskets, for trading and for position data. And then alongside that, you have your core banking systems, loan data, customer data, and then you might even have external data. You might have external data for market prices, for historical information, or other macroeconomic data that you bring in externally. And the graph can naturally, because of its data model and its approach to managing connections, can handle the connections between all those different data types very easily, right? So it avoids having to create a traditional data warehouse, bring all of that data together into a relational structure in one place. Instead, you can use the graph to connect that data from all these different sources and then query it again at scale in a very operational way. This really allows you to to leverage your data to maximum effect, right? Rather than being just discrete scattered bits of data, you've now connected it, you understand the connections, you can leverage the additional context and richness that those connections bring to your view of your data. And it allows you to really move from just having some information and some data lying around to being able to generate true insight and true wisdom from your data. And again, doing this in a real-time way rather than a batch, in a batch fashion or map reduce or something like that, being able to do it in real time. And when you have this sort of a highly connected view of your data built, it really enables you to to meet the requirements of a modern risk management platform. Right? You can tie together all these different data sources and then bring some additional tooling to bear. Right? So some Neo4j solutions for risk management and compliance, perhaps some graph analytics to understand more. Maybe clusters or pathfinding within your data, and being able to span all of those data silos that you used to have, and being able to then put that tooling on top to be able to generate your view of risk and your compliance is really, really valuable, and it can take you from a place where you're approaching compliance for FRTB or any of the other regulations, from just being a regulatory spend and something that you need to do the minimum to be compliant, and instead turn your data into an asset. Right? Once you understand all of your data in this way, you can use it for so much more than just regulatory compliance, right? And it also allows you to then leverage this platform for your operational risk management as well within your own business processes. And building a system like this really puts you in a position where you're future-proofed, right? As more regulations come down the pipeline, as they always do, they all will have some aspect of understanding your data lineage, and being able to do that reporting to the regulators on that. So once you have this view of your data, you're really in a much better position to be successful in compliance efforts for future regulations. So before we look at the demo, we'll just touch a little bit on the property graph, which is Neo4j's model for the graph, and our Cypher query language, so that for anyone not familiar with these, the demo makes a little more sense. The property graph database is made up primarily of three things. So there's nodes, And in our example here, the nodes are circles. We have two types of nodes, two labels for nodes in our database. We have person nodes, so we have Anne and Dan, and then we have a car node. And these nodes can have properties associated with them, any number of properties associated with them. These properties are really just key value pairs. So we can see the person on the left, his name is Dan. He was born May 29th, 1970. And he has a Twitter handle @Dan. And then on the right, we have a person named Anne, who was born December 5th, 1975. We don't have Anne's Twitter handle, and that's okay. Neo4j doesn't, out of the box, enforce a schema in the same way that a relational database does. You can have different properties, different types of properties associated with nodes that have the same label, and that can grow and change over time. So it really enables a very agile, iterative approach to setting up your database. Between nodes, we have relationships. So we can see we have loves relationships, we have lives with relationships, we have a drives relationship, we have an owns relationship. These relationships can also have properties associated with them. So we can see that Dan drives the car that Anne owns. He's been driving it since January 10th, 2011. Now, when Neo4j saves, persists a relationship between two nodes, it always does so with a direction for that relationship. And sometimes that direction is very important and sometimes less so. So, for example, Dan lives with Anne. And if that's true, you wouldn't really have a situation. It would be logically impossible for Anne not to live with Dan, right? So in that case, the direction is a little less important. However, we can see Dan loves Anne, and it's more important, I think, to understand that relationship. So luckily for Dan, Anne also loves him, but it would be entirely possible for Anne not to love Dan, for that love to be unreciprocated, in which case, the direction of that relationship would be very important to understand. And those simple building blocks are really what make up the property graph database and enables the richness and power of Neo4j, which we'll see in a few minutes. And then just to wrap up our overview, we'll take a look here at an example of Cypher, which is the query language for Neo4j. Cypher is designed to work with graphs, and so some bits of it feel familiar if you know SQL, but also it's quite distinct and separate from SQL. So here we have match, which is sort of similar to a SQL select. We're looking to match a node in the database. In parentheses, or the rounded brackets, we have the elements of the node that we're looking for. So we represent the node with the parentheses. Colon person represents the label we're looking for. So we're looking for a person node, not a car node. And then in the curly braces, we have the key value pair. Name is Dan. So that's how we identify the node that we're looking for. We then say that we're looking for who Dan is married to, and we represent that relationship with square braces, square brackets. Again, colon married to represents the label for that relationship. So who is Dan married to? And we sort of draw the direction using the dash and the greater than sign to show that it's an outbound relationship, married to. We could change that direction to and show with the less than dash before the married to bracket, showing who's married to Dan that way, or you could leave the greater than and less than sign off, and that would be a bidirectional query. And then at the end, we have another node inside parentheses, but we don't specify any matching information there. We just put a variable, the name spouse, so that any information that comes back about Dan will be held in that variable, and we can then work with it additionally in our query if we want to. Okay, so with that, we'll jump over to a demo. What we're looking at here is something that we call Neo4j Bloom. Bloom is an end user interface for Neo4j. So anyone who's familiar with Neo4j for a while might recognize the browser interface, which is something that ships with every installation of Neo4j. But it's really query driven. To be able to use it, you need to know Cypher, which isn't always an option for business users or for everyone. Someone who's just coming into the graph database world fresh. might take them a while to get to the level of fluency with Cypher that they would need. So instead, Bloom provides a much easier interface, and it's all driven by a search bar here. So we'll see different ways that we can interact with the graph database using Bloom without necessarily having to write a bunch of Cypher. So first, if you look here on the right, on the upper right, you can see a bunch of colored lozenges. These represent the different types of nodes we have in the database, or the different labels for nodes. So we have trading desks, we have basket in purple, we have equities in green, we have price nodes, and then we'll have alerts. We don't have any in the database now, but we'll create some on the fly in just a moment. So first, if we take a look at trading desks, I can start typing in trading desk, and it matches the blue color for trading desk nodes. If I pull those back, we can see we have 3 trading desks in the database. There's the technology desk, the energy desk, and the transportation desk. We can also see each one of them has a rating. If I drill into that, double click on that node, I can see the risk score for the technology desk right now is 0.06. The energy desk is 0.02, and so is the transportation desk, 0.02. And then again, as we import data over time, these risk scores can be updated and refreshed accordingly. Taking a look at the relationships section here, we can see all of the relationships for this technology desk node. We can see that it has a position in 3 different baskets. And then if I click on neighbors, I can see some details of the nodes that sit at the end of those relationships. So the neighbors are all of the nodes that are directly connected to the technology desk. And this shows me the detail of each of them. So we can see that there's an internet basket with a risk score of 3.69, an artificial intelligence basket with a risk score of 0.63, and a technological innovation basket with a risk score of 3. So if I clear that, one of the other things Bloom lets you do is, as a developer, you can define some more complex Cypher queries and then hide them behind a very simple search phrase, right? So in this example, we're going to take a look at the lineage of a particular equity, and you can see here is the Cypher that fetches that. But your users, again, might not have that complex understanding of Cypher, and so instead we're just going to type in lineage of, and then the $ name represents a variable. When we enter a value into that, it fills it into the Cypher, and then we get the results of our query without actually having to type the Cypher for it. So we can take a look at lineage of, and then we can take a look at the lineage for NVIDIA Corporation. So here we can see NVIDIA in the middle in green is the equity. NVIDIA has the last risk score for NVIDIA is 3.45. We can see its current price. 3.6 is the risk score now. We can see its ticker symbol and some metrics as to the yearly high risk score and low risk score. And then we could also see that 2 baskets have a position in NVIDIA. So we have the electric and autonomous cars basket and the artificial intelligence basket. And then there are 2 trading desks associated with those baskets, transportation desk and the technology desk. We can also see the artificial intelligence basket has a position in electric and autonomous cars. And around NVIDIA, we can see different price nodes. So for different dates, we can see what the price was for that particular equity. So this gives us a temporal view. We can see over time how that price has changed, and then how that might affect the overall risk and the positions of the baskets and trading desks that ultimately hold NVIDIA. We can also show, going the other way. So rather than looking at the equity and the lineage all the way up, we can see the lineage for a particular trading desk. So we can see the lineage of, say, the transportation desk. Okay. So again, here in the middle, we have the transportation desk. And then we can see as we look through the graph, we can see all the different baskets that has a position in, the relationship of those baskets to other baskets, and then ultimately, what are the equities that sit underneath that, right? So again, being able to do the lineage in both directions, finding a desk, and then going all the way down to the individual equities that sit underneath that, the individual assets. And then in reverse, looking at an asset and being able to look at how its risk is aggregated all the way up ultimately through baskets and trading desks. Okay, so now what we'll do is we'll import some new data. So we'll simulate, market event as data changes throughout the day. Obviously markets never sit still, so you'll need to refresh this data in real time, be able to manage your risk in real time. So here we're going to simulate some changes in the risk score for individual assets and look at how that aggregates up through different baskets and different trading desks. And we'll also generate some alerts, right? So we're interested if a risk score changes by more than 30%, we can set up some alerts in the system. And then that, of course, could feed into some sort of a UI or some sort of an alert system for the people that manage these desks so that they're aware of these significant changes. So here we're just importing from a CSV. We've added 28 new nodes, each of them with one label. We've set 649 properties. We've created 28 relationships. And that took, just running on my laptop, 1,924 milliseconds. Okay, so now I'll just refresh Bloom so we can get the new data in. And we'll take a look first at some of those alerts. So here we've got the 28 alerts that we've created, and we can see, for example, if we take a look at FedEx here. So the risk score of FedEx has increased more than 30%. We can pull up the node for FedEx. As you can see, this alert pertains to FedEx. Its risk score is now 9.26. The last risk score was 5.47. And so the difference between 9.26 and 5.47 is more than 30%, which is why we've raised this alert. And this could happen throughout the day, and then you could react to alerts in whatever fashion is appropriate for your business processes. And ultimately, because these alerts are linked to individual assets, again, you can then understand how those alerts then cascade through their baskets and then ultimately up to individual trading desks, right? So we can see that the change in Micron technology would affect the overall risk rating for the artificial intelligence baskets. And then ultimately there's one trading desk that sits on top of that, as well as another basket, right? So anybody who's interested in these events would be able to follow the lineage of that change and see directly how that change gets modified. Okay, so now if we're interested in analyzing the relationships between our trading desks and our baskets, right, maybe we need to understand how risk might affect multiple trading desks and multiple baskets at a time, or maybe we're interested in the structure of our baskets and trading desks. We can see very easily in the graph how these things are connected. So we can see the connections between trading desks. Right, so again, in blue we have our trading desks. And then we can see all the different ways that those trading desks are connected, right? So what are the baskets that they share in common? For example, we can see the technology trading desk is connected to, directly connected to the internet basket, the technological innovation basket, and the artificial intelligence basket. The artificial intelligence basket has a position in the electric and autonomous cars basket, which is connected to the transportation desks as well, right? So in this way, we can understand how our trading desks are connected, and if we need to take action to reduce exposure, to manage the risk that would cascade between them, we can do that by understanding the structure and being able to see it very clearly. And then we can also, of course, report this to the regulators as well. We can also see within a trading desk how interconnected things are, right? So we can see the connected equities in, for example, the technology desk. So again, here in blue we have our technology desk, and then we can see within it there's a number of connected entities, right? So we've got the technological innovation basket, which has a position in Amazon. Several of the other baskets under this trading desk also have positions in Amazon. So we've got the internet index, we've got artificial intelligence basket, we've got cloud computing, right? So that one asset sits underneath the technology desk and through a number of different paths. And then ultimately, you may decide to rework some of those baskets so that fewer of them are exposed to changes in risk for Amazon, for example. Okay. We can then also use Neo4j just to do some more straightforward MI type reviews. So we can see, for example, the top 5 highest risk baskets. Right, so just going away and looking for the baskets with the highest risk scores. And then if we wanted to, we could start to see how some of these things, again, are interconnected. So we can see the internet basket has a position in the internet basket. The internet index, I mean, we can also see how some of these cascade up to trading desks, right? So again, if you're interested in just looking at the highest risk baskets in your organization, you can then start to navigate some of the relationships between them and understand how these things are connected and how risk might move between these different parts of your business. We could also see the riskiest equities. So we have the top 10 riskiest equities. We can see here in the list, Amazon has the most risk. Right? So it's the way risk was calculated for this, was fairly simple. In real life, organizations might have a more complex approach to doing this, right? But we've basically just looked at how often the price changes for a particular equity, and that fluctuation is kind of a proxy for risk, right? The greater the fluctuations and the more of them, the higher the risk is for that particular equity. And then again, we could start looking at the different entities that would be affected by this, right, and how they're related to each other, and then ultimately all the way up to a particular desk. if we wanted to understand a little bit more about how the risk is generated, we also have a number of queries, pre-written queries that we could use to look at this. So we can see the top 5 equities with the highest price movement, right? So these 5 assets have had the highest movement of price in the database. We can also see the ones with the highest risk movement, so where the risk score has changed the most. And we can see there isn't any overlap, right? The 5 equities with the highest risk movement aren't the same 5 that have had the highest price movement within the records in the database. But if we look at the view of combined, so the top 5 equities with the highest price and risk movements, we can see there is some overlap, right? So Twitter and Netflix had the highest price movement. FMC Corp and Editas Medicine had the highest risk movement. And then we've got Amazon and Nvidia, which fall into the category of both the highest price and highest risk movement. And then again, from there, we can always take a look at the overlap between them, right? So we can drill into them and understand how the risk for these things moves throughout the organization, how they're connected, and what that might mean for your organization, right? So we can create quite a big visualization on this. If we expand everything outside of these individual nodes, we can see all of their price movements. We can see the baskets that they're associated with, right? And then from there we can continue to move through the hierarchy. Here we've even got an alert. So in the last data import we did, Editas had a risk change of more than 30%. Right, which sort of underlines the fact that they showed up in the query for the most risk and price movements in the database. So hopefully that's given you a view of how this sort of data can fit into a graph, and how putting it into a graph can help you understand how all this data is related, how you can follow the data lineage both down the chain from trading desks all the way to individual assets, and then the other way back up from individual assets all the way up to the trading desk. And it's quite a visual, easy to understand picture that you see, which means it would also be easy to understand for the regulators, right? So it makes reporting quite easy and quite straightforward. So just to recap, we've seen how graph technology really quite uniquely can address the requirements for a lot of recent regulations, right? We've really focused on FRTB, and we can see that we've ticked the boxes for FRTB. We can show data lineage, we can aggregate risk in real time, we can view data over time, so we have temporal consistency. We can take a view of data at any point, any snapshot in time. We can calculate risk based on the data that we have. We can visualize it, making compliance reporting and governance much more straightforward. And these same requirements apply to a large number of other regulations. So BCBS 239 is very similar, MiFID 2, GDPR even. So again, having your data in this format for one regulation really puts you in a good position to be able to be compliant with a number of other regulations. Right. And lots of other people, agree that using your data in this way is a really good idea, right? So there's a McKinsey study and a Basel study which found that 70% of banks cannot adequately explain the profit and loss statement and its drivers, right? Which is bad news. So by implementing a system for FRTB compliance in a smart way, it really puts you on a good footing to manage your own business, right? Rather, as well as just being compliant for particular regulations, right? And this is a great opportunity for banks really to be able to leverage exciting new technology like graph databases for regulatory compliance as well as for day-to-day operations. Okay. So hopefully you've seen that Neo4j really is a great fit for risk management and compliance, managing highly related connected data in real time, tracing data lineage, visualizing that information, and really creating a system that can be used to help manage trading, fund management, pricing, and other data silos into one unified data set that can help you not only be compliant from a regulatory standpoint, but also put you in a great position for your day-to-day operations and running your business. And with that, we're ready for some Q&A if we have any questions.
Yeah, great. So just to kick us off, you did the demo using our new tool, Bloom.
Mm-hmm.
So for companies with a particularly large data set, are there any kind of limitations to the number of nodes you can be using?
So Bloom is much better at handling large visualizations than the Neo4j browser is. I would say Bloom is probably optimized for visualizing nodes that you would measure in kind of the tens of thousands. Right? 1 million nodes in one visualization, it will be difficult, but I would also probably suggest that doing, as a human, being able to understand 1 million nodes on one screen isn't really that valuable anyway. So I wouldn't say there's a limit per se. Certainly the hardware that you're running on would affect it. It would require a better graphics card maybe to be able to handle super large visualizations, but being able to visualize graphs or subgraphs, in the range of tens of thousands of nodes is certainly viable.
Okay, and are there any plans really to integrate machine learning into Cypher or to use it for this type of use case so that you could perhaps run a simple regression rather than doing offline analysis?
So the Cypher language is always growing. I wouldn't say that I'm aware of any plans necessarily to implement machine learning directly in Cypher, but there's certainly a lot of extensions to Cypher, either community developed or written by Neo4j that would aid that, and certainly you could extend this set of functions with your own. So we do have a number of graph algorithms for centrality and pathfinding and community detection that you can run from a Cypher command that will allow you to get more insights into your graph. And then of course, we are also working on things like integration with Spark. So there's a product called Neo4j Morpheus, which allows Cypher to be run on Spark, and also to integrate with data from the rest of the Hadoop ecosystem, so Impala or HBase or HDFS or what have you. So you could pull some of the data in the graph into Spark, and do some of your machine learning type work there as well.
Okay, and a lot of your demo was kind of based around visualizing the data lineage of your nodes. But do you know how you might be able to link in risk calculation models?
So you certainly could extend the graph model that we have, the schema, for lack of a better word, to demonstrate what calculations were used there and how those calculations are governed. So if I understand the question correctly, how can we link individual metrics back to a calculation and understand how that calculation is governed? So you definitely could extend the graph model to include those calculations, what version of the calculation was used, when that calculation was invoked to create a particular metric. All of those things could also be represented in the graph.
Okay. And with Neo4j, is it possible to change the model very easily? For example, adding nodes or editing relationships?
Absolutely. So because out of the box, Neo4j doesn't enforce a schema, it makes that sort of iterative approach to working with your data very easy. It's very easy to add new types of nodes, to add new properties on those nodes, to add new types of relationships. And often what you'll see is several models layered together within the same graph, right? So you might have different types of relationships that you're only interested in for particular queries or for a particular view of your data. And you can have all of those living together quite happily inside the graph, as you're importing new data in. So it is quite flexible and very agile if that's the way that you work.
And is it possible to capture bits from Bloom or from your graph into kind of an editable representation or presentation, I should say, or a report?
Sure. So I think a very straightforward approach would, of course, be to take a screenshot or capture a snapshot of what's on your screen when you have the graph looking the way that you want to. You can also copy, if you in Bloom copy a selection from the graph, that will export the Cypher to create that graph again, and then you could pass that to people, or you could in the Neo4j browser, load that Cypher up again. The version that we're looking at now of Bloom is still 1.0, so it's a very young product for us, and as the product roadmap evolves, there will be new features built in, and I'm sure some of that will include being able to export, a JPEG or a PDF or something like that directly from the screen.
Right. So if you're dealing with a particularly large graph, what kind of latency should we expect, or what's kind of the response time from Neo4j to do an aggregation on, let's say, millions of nodes?
Sure. So Neo4j, because it is a native graph database, being able to work with large data sets and deep, path traversals where you're traversing multiple hops, right? Not just one hop or two hop, but 10 hops, 100 hops, whatever that might be. It's built to scale on those sorts of queries very well, right? It does depend on your data model. I couldn't give an exact latency figure, but certainly, even though we're looking at a small graph today, you can see, even just running on my dual core laptop, it's quite responsive. In terms of being able to return that to the screen, it varies, right? If you have a very large visualization, then the amount of data that you're transferring from the Neo4j database to the web client, because Bloom just runs in a browser, if that's a really large set of data, then it might take a while to visualize. But typically, if your model is effective, if you've got the right sort of relationships between your nodes and you've got the right indexing, you're taking the right approach to storing your data and then doing your calculations, normally you should expect, even if you're talking about millions of nodes, pretty snappy response times. Millions of nodes for Neo4j is not something I would consider a very large graph, right? Millions of nodes is kind of a medium range for us. Large graphs in Neo4j would be many billions of nodes and many billions of relationships.
Wow, okay. And if you're kind of moving over from a relational database, how easy is it to kind of migrate the data stored in a relational database over to Neo4j?
There's a number of ways to do it, and it's usually fairly straightforward. There is a mapping exercise that needs to take place, right? So you need to understand the model that your data is in your relational database and how you want that to map into Neo4j. So what becomes nodes in your graph, what becomes relationships, and what become properties. So once you have that mapping in place, there's a number of ways you can do it. Neo4j has tooling that we ship with Neo4j to directly connect to SQL databases and pull that data out. You could write to CSV and then import that CSV into Neo4j. You could use an ETL tool. So we work quite a bit with Kettle, the open source data integration tool, but a number of other integration tools have plugins for Neo4j. Or we do also have a visual ETL tool that we have, which will connect to your SQL database, will allow you to visually do that mapping. So you can say what becomes nodes, what becomes relationships, what become properties, and then that tool will write your CSV files and do the import for you. Right? So the mapping exercise, I would say, is probably where the most work goes in, because you really want to try to get that right, so that your graph is accurate and contains the right data in the right format. And then actually doing the import should be fairly straightforward.
Makes sense. And then once that data is into Neo4j, is it stored in the cloud or remotely? How is that?
It can be stored anywhere, really. So Neo4j is definitely cloud ready. Neo4j runs anywhere you can run a JVM. It can run on Linux, Unix, Mac, Windows, what have you. It can run in the cloud. It can be run on-premise. It can be run in containers, or it can be run in some mix of those, right? So if you've got a cluster, some of your cluster members can exist in the cloud and some can exist on-premise. It's really quite flexible.
Okay. And is it possible with this sort of use case to perform what-if analytics? For example, if you wanted to know what would happen to your basket if you applied a change of equity prices by 5%?
Yeah, absolutely. It's really good for doing that sort of thing, for doing what-if analysis, modeling various scenarios and what might happen. And there's probably a couple ways that you could go about that. You could actually create a new version of your graph, run your calculations, put that information into a new version of the graph so that you can compare the two. You could put it into a new set of properties or temporary properties, or there's even functionality. Neo4j has a library of functions that's called APOC, which is downloadable and freely available. And in that set of functions, there are functions for working with virtual graphs. So you can run your calculations and return to the browser a virtual graph that isn't actually saved anywhere in the database, but has been created virtually as an output of your queries. And so that would, again, allow you to do your what-if analysis to see what would happen if a particular equity, changed price or changed its risk rating. How would that cascade throughout the system so that you could view that and respond accordingly.